A control system selects an action from an admissible set, subject to a loss function defined over an uncertain input. The formal objective requires specifying a relationship between actions and the uncertain environment. In the probabilistic formulation, this relationship is expressed through a fixed probability measure over the input space. The selected action is optimal only under the specific measure assumed during design. When that measure deviates from the true generating process, the optimality guarantee dissolves with it. The probabilistic control objective minimizes the expected loss over a distribution P on the input space. This formulation requires P to be fully specified before design begins. Tail events, those at the extremes of the distribution, are weighted by their assigned probability mass. As that mass approaches zero, the contribution of the extreme event to the objective vanishes. The system is therefore designed to be optimal on average, not robust to the worst case. The robust control objective replaces the expectation over P with a supremum over an uncertainty set theta. The selected action minimizes the worst-case loss across all parameter configurations within that set. No probability measure is required. The uncertainty set specifies what the system must tolerate, not how likely each scenario is. The adversarial extremum governs design, not the average. This structural substitution changes the nature of the optimality guarantee entirely. The probabilistic objective integrates over the sample space, weighting each outcome by its assigned measure. The Minimax objective takes the supremum over the uncertainty set, assigning no weights at all. These two operations are structurally distinct and do not generally produce the same control action. The probabilistic design is optimal under its assumed model. The Minimax design is optimal under its worst-case model. Selecting between them is a structural choice about what kind of guarantee the system requires. When the assumed probability model diverges from the true generating process, the probabilistic controller remains confident, but in the wrong system, its action is optimal under a model that no longer applies. The robust controller is immune to this failure mode because it makes no commitment to a specific probability measure. The uncertainty set theta captures what must be tolerated structurally. Conservatism, accepting reduced nominal performance, is the price paid for this immunity. Robust control guarantees performance for all realizations within the uncertainty set theta. This guarantee holds only as long as the true system parameter remains inside that set. If the true parameter falls outside theta, the robust guarantee fails, just as the probabilistic guarantee fails under misspecification. An unbounded uncertainty set produces guarantees that are impossible to satisfy, collapsing the design into infeasibility. The robustness of a system is therefore only as strong as the uncertainty set used to define it.